Hello, everyone. So this is a joint work with my advisor, Professor Charlie Hu and Professor Xiaojun Lin. And it's about a Coflow scheduler called as Fillet. The big data analytics jobs are being used in diverse fields. And according to an estimate by Statista, it is going to be a $100 billion market by 2022. And an example of such a job could be a MapReduce job, which has two compute stages, map and reduces. And the map stage communicates with the reduce stage in the shuffle phase. So the communication phase in such jobs has a great impact on the job performance. For example, a statistics based on a Facebook trace has shown that jobs spend around 25% of time in communication. And hence, to speed up jobs, it is quite important to optimize their communication phase. Also, previous studies have shown that when the key to speed up the communication phase of big data jobs is to optimize or improve the collection of flows and not individual flows involved. So this leads to a Coflow abstraction. Basically, a Coflow is a communication abstraction for data parallel applications to express their performance goals. Or in simple terms, you can say that Coflow is a collection of all the flows that share common goal. So in the example of MapReduce job, we can say that all the flows in the shuffle phase can be termed as a Coflow. And the Coflow will not finish until all its flows finish. So what this means is that the Coflow completion time is the completion time of its last flow. Now, in a shared cluster, there are many jobs competing for resources. Let's look at an example where we have two jobs, a blue job with 2 mappers and 2 reducers, and an orange job with 4 mappers and 2 reducers. So all the flows in the blue job make Coflow 1, and all the flows in the orange job make Coflow 2. And these Coflows are competing to share data center network. So this leads to the interesting problem of non-clairvoyant Coflow scheduling, where jobs are arriving online, and flow sizes are not known. And recent work has shown that there are a lot of practical challenges in assuming that flow sizes are known. And the goal of Coflow scheduling is to minimize the average Coflow completion time. So the task of online Coflow scheduling can be divided into 2 steps. For example, the first step, we need to learn the Coflow sizes. And then second, schedule them as per our need. So the problem has been studied in the past, and several online Coflow schedulers like SATS, Graviton, and Allo have been proposed. They use priority queues for learning the sizes, and they use the priority queues to schedule them as well. But learning by priority queues has several drawbacks. And so in this paper, we propose a new online Coflow scheduler called as Fillet, which uses sampling to learn the Coflow sizes. And this makes Fillet also very scalable by nature. And then Fillet uses priority queues to schedule the Coflows. So with this background, going forward, we'll first look at the existing approaches towards Coflow scheduling, then their drawbacks. Then I'll talk about our proposed design, its key observations involved into it, and the challenges we faced. And finally, we'll look at the evaluation. So to understand the core idea in the existing Coflow schedulers, let us start by looking at an example which illustrates how multiple priority queues have been used in learning job sizes online in single CPU system. So the key idea is that have multiple priority queues, and with fixed execution quanta for each queue, then increase the execution quanta with decreasing priority, and start all the jobs from the highest priority queue. And if they do not finish within the queue's quanta, move them to a lower priority queue, and make room for new jobs in the higher priority queues. So to understand this, let us look at an example with 3 jobs, J1, J2, and J3, of unknown durations. I'm showing the durations on the slide just for reference, but we do not know them while scheduling. And let's have a 3 priority queue structure, with Q0 being the highest priority. So all the jobs start in the highest priority queue, Q0, and the J1 gets scheduled first. It finishes, so it's well and good. Then we schedule J2, which does not get finished within the quanta of Q0, so we move it to a lower priority queue. Then we go for J3, and we keep doing this until all the jobs finish. So what we can see here is that the shorter jobs are finishing in the higher priority queues, and longer jobs are slowly and gradually being moved to lower priority queues. So this is an approximation of the shortest job first. And similar sort of idea is used for Coflow scheduling. But the illustration we saw was just for a single CPU and single CPU system and single one-core processors. But Coflow has many distributed flows on different ports. Just as shown in this example, the red Coflow C1 is spread on both the ports. So to extend the idea of learning by multiple priority queues to Coflow scheduling, the existing schedulers like Saath, Graviton, and Allo replicated the priority queue structure on each port. And they used the total data transmitted by a Coflow as the progress of notion, used a global coordinator which tracks the progress of Coflows at each port, and then assigns them to priority queues based on their progress, global progress. So there are several drawbacks of learning by priority queues. And we will discuss the two primary drawbacks here. So let's start by looking at them one by one. The first drawback is that jobs pay an intrinsic overhead while transiting the queues. Let us consider a simple example here with two jobs, with J1 of duration 32 seconds and J2 of duration 16 seconds. Both the jobs arrive at the same time in the order J1 and J2. So if it would have been perfect SJF, J2 will finish in 16 seconds. It will go first and finish. But however, in the process of learning sizes using queues, it has to transit through Q0 and Q1. And as you can see that in each of the queues, it will be blocked by J1. So this makes its completion time to go to 32 seconds. The second drawback is that jobs of similar size will end up doing round robin, and which is known to be the worst case for minimizing average completion time when the jobs are of similar size. So in this example, let us consider that J1 and J2 are of same size, 32 seconds each, and they arrive at same time in the same order. So now in the normal SJF, either one of them would have gone first and then the other one. So the average completion time would be 48 seconds in this case. But now what will happen, their execution will get interleaved. And both of them will block each other in each queue, and the average completion time goes down to 56. So both the drawbacks we saw are intertwined, and to measure their impact on CCTs, we did an empirical measurement. We measured the ratio of time spent in learning by Allo. That is the time it took to reach its correct priority queue. And what we found is that 40% of the coflows which moved beyond the first priority queue spent 20% of their time in learning. So in this paper, we propose a new online coflow scheduler, Fillet, which uses a novel approach for learning coflow sizes online, which overcomes the previous two drawbacks I described. Let's look at the details of the observation. So Fillet's design is motivated by following two key observations. The first one, that a coflow has many flows. And second, sampling is an effective technique to estimate average. Now, combining these two observations leads to a natural way of new online learning technique, that upon a new coflow arrival, we sample few flows from it and schedule them at high priority. And then we use the observed size of the sampled flows to estimate the size of the entire coflow, and then the rest of the scheduling follows the same priority queue structure and goes the same way. So just to recap, in the new scheme, we changed the learning technique instead of using multiple priority queues, we use sampling. And we retain the same second step, that is, we still use multiple queues for scheduling. Now, we know the overview of Fillet's design, and it will work well if the idea of sampling goes well. But I know that you have several doubts about effectiveness of sampling, so let us start looking at them one by one. And the first doubt which comes, that since we do not schedule other flows of a coflows till sampling flows are finished, so we may naturally doubt whether this will delay the other flows of the coflow. And my answer is no, it will not delay, because there is always some congestion in the cluster, so jobs anyways have to wait. And but then the next question is that the sample flows are scheduled with very high priority. So are they going to delay the flows of the already transmitting coflows? Yes, it might. And to solve this, what Fillet does is it just samples 1% flows for sampling and learning the size. So now this raises another doubt about sampling, that how accurate will the sampling be when we are sampling just less than 1% of the flows. So my answer is going to be in two parts. The first part is that if there's low skew in the flows of all entire coflow, then we have no problem. Now the second case is when there is high case, when there is high skew. So let us consider this in two cases by looking at a simple example of two coflows, C1 and C2. In the first case, let us consider that they have a considerable difference in their length, where C1 is of 10 units and C2 is of 2 units. And since there's high skew, we might end up making some certain amount of error. But let's argue here about an extreme case of error. Let's say we make 30% error in C1, and we estimate its size to be 7. And we make 100% error in C2, and we estimate its size to be 4. But still, C1 will remain larger than C2. And so the order will not get flipped. And so if scheduling order is not flipped, it will not impact the CCT. Now let's consider another case where their sizes are similar. C1 is of 4 units, and C2 is of 5 units. So if C1 goes first, then the average CCT will be 13 by 2. And if C2 goes first, then the average CCT will be 14 by 2. So in this case, if we make certain error, and even if the orders get flipped, it will not impact CCT much. So this completes the first step of the scheduling, that we learned the size. Now the next step is to place the coflows in the right priority queue. So trivial approaches have been to order them on basis of their total size. But with coflows, there is one issue, that they are spread on multiple ports. They are distributed in nature. And different ports might have different level of contention. So to account that contention, we use least length-weighted total port contention. In the interest of time, I'm going to skip details of this. Please refer to paper for this. Now we face some practical issues in designing Fillet. The first one was to provide starvation-free guarantees. Now, since we are using priority queue structure in Fillet to schedule the coflows, so we assign weighted. We do weighted sharing across the priority queues. So each queue gets some share continuously of the bandwidth, and within each queue we do FIFO. So this guarantees some execution for each coflow. Now the next issue was that since Fillet is going to sample flows and then schedule the other flows, so what if their coflow has just 2 flows? And if we do sampling, then it might end up serializing its flows. So that could have a very high cost on CCT. So for this case, what we do in Fillet, we sample coflows which have at least total number of flows beyond certain threshold. And the default threshold we use was 7. Then another issue is of work conservation. Fillet do not schedule non-sampling flows till sampling is finished. So such a situation might arise in cases where there is no other flow at the port to be scheduled. Even if there's data, but there's no sampling flow to be scheduled, and this coflow is still under sampling phase. So in such cases, not to waste resource, we do, if there's only one flow at the port, we do schedule them. OK, now let us look at the evaluation of Fillet. Let us start looking at the speed up achieved in coflow completion time by Fillet. So for this, we evaluated Fillet using 2 different traces. First, a publicly available Facebook coflow trace. And then using that Facebook coflow trace, we derived another trace with, to match a skew to a Microsoft data center reported in a paper in 2010 in OSDI called as Mantri. So we can see that Fillet speeds up coflow completion time on both the traces over existing scheduling approaches. And in particular, if we look at Fillet speeds up over Arlo by, the average CCT improves over Arlo by 1.51 times for the Facebook trace and 1.36 times for the Mantri-like trace. And one of the reasons why Fillet significantly speeds up the coflow is that it considerably reduces the learning time. So when we measured here the time spent in learning by each coflows, we found that in Fillet, only 7% of the coflows that moved beyond highest priority queue spent more than 20% of their CCTs in learning, which is approximately 6 times lower than allo. Now, CCT speedups translate to job speedup as well. And for this experiment, we used the Facebook Coflow trace and kept the job distribution same as that used in the allo paper. Fillet improved the 90th percentile job completion time by 7.87 times. Using sampling to learn coflow sizes is much more scalable than using multiple priority queues. We did extensive qualitative and experimental analysis to show this. I'm skipping the details here due to lack of time, but please refer to the paper for details. A particular result I would want to mention is CCT speedup achieved over 900 ports experiment. So using the 150 port Facebook Coflow trace, we derived a 900 port trace. We replicated the 150 port trace 6 times across ports. And we can see that Fillet improves average CCT by 2.72 times over allo for the 900 ports, whereas for the 150 ports, it was 1.5 times. So at scale, Fillet's performance is even better. We also evaluated Fillet's sensitivity to parameters like limit to bypass the thin coflows, the priority queues parameters, that's the threshold for the first queue, what's the growth factor for the priority queues. And the result shows the Fillet is quite robust to variation in these parameters. So in summary, state-of-the-art Coflow schedulers use priority queues for learning, but learning by priority queues have a very high overhead. And in this paper, we demonstrate a new online learning technique, which shows that sampling can be a very highly effective technique to learn Coflow sizes. And this also makes Fillet is an inherently scalable design. So on 150 nodes data center, simulated data center, Fillet speeds up over allo the average Coflow completion time by 1.5 times. And over 900 nodes, it speeds up by 2.72 times. Thank you.
Hi, Marius Koga, CPFL. Great talk. So you might blame me that I'm biased, but I can take the blame. I'm trying to understand, you try to guess the coflow sizes, or you're trying to estimate this. But isn't this an outcome of the fact that TCP masks all this information in a way? Because at the beginning you talked about MapReduce jobs that have some specific communication. Aren't those RPCs? So if you were to have these RPCs, and in most cases you know the request or the reply sizes ahead of time, could you do something there instead of just trying to battle TCP and trying to be smart and guess things?
Yeah, so if I understand the question, basically you're trying to say that by application or by the existing mechanism, we can already know the flow sizes going on.
Or the coflow sizes.
Or the coflow size. This is a debatable thing, but it's in practical situations, it's not always possible. Because in some cases, when you're implementing the application, some applications might be telling, some applications might not be. The flows are being transmitted, they are generating, and data is being transmitted. Many times it's not immediately done. There has been a recent work I can show you that. So there has been a work recently in NSDI, which has shown that what are really the practical challenges to know flow sizes in advance. So yes, some problems are solved assuming offline the flow sizes are known, but really practically it's not possible in many cases.
Thank you.
Hi, I'm Alan Liu from CMU. Really great talk. So I think that sampling is really a, efficient way to estimate the average flow sizes on Coflow. But my question is, it reminds me to the work back to SIGCOMM 16 as Coda. They actually claim that they can online learning the size of Coflow sizes, right? And then schedule based on that. So do you have any comments about how you compare with them, or do you have anything to compare with them? Because I think you just compare with Allo. Do you have any? Coda was not more about learning sizes, but Coda was also like, if the flows are there, how do we know which flow, which part a particular flow is, to which coflow the flow belongs.
and Coda's focus was more towards mapping the flows in the coflows online.
But in terms of scheduling, are you doing better than them? I mean, or it just the assumption is totally different. You aren't assuming any information about the flow.
No, we are assuming that flow size is not known, but we are assuming that we know which flow belongs to a coflow. So we know that
I see.
these flows are part of coflow 1 and these flows are part of coflow 2. Coda does not assume this. Coda is solving, so it's solving a completely orthogonal problem.
Okay, I see. Thank you.
All right, let's thank our speaker again.